Having reviewed this basic concept of electric potential, I would now like to show you several things that it's very useful for accomplishing. Now, before I go to do that, first I'd like to convince you that it's actually a relatively easy quantity to calculate. And to do that, I'm going to do it in a series of steps. First, I'm going to show you what the electric potential is like for a point charge. Then I will show you a principle of superposition for calculating electric potentials. So if we go ahead and apply this then to the concept of a point charge, so this would be electric potential, this topic, electric potential for a point charge. We can use the result that we had previously for voltages from point charges. You will recall from what we have immediately here, that is that the potential then for a point charge at location X is going to equal the voltage due to that point charge as we move a test charge from the reference location over to location X. So the situation then looks something as follows. There's our point charge here, Q, that is responsible for the electric potential that we're trying to calculate. There is the point X at which we are trying to calculate the electric potential. And then you see we need a third point. We need our reference point. Now, there is a standard assumption or definition for reference point. For all electrostatic problems, we take the reference situation to be where all of our charges have been scattered, all moved away off to infinity at very large distances from each other. And we call that the situation of zero potential energy. That means then that our reference point, it's kind of hard for me to draw it on our piece of paper, but our reference point is going to be very, very far away. So I will indicate it by an arrow pointing some distance very, very far away, going off towards infinity. So our job then in calculating this potential for this electric potential at location X is to compute the voltage due to this point charge when I take an object from this infinite distance very far away and carry it through from infinity across some path that finally brings me to the location X. Now, previously, we had worked out a formula for the voltage associated with a charge. And you will recall that it went something like this. It was Coulomb's constant times the charge times then a quantity, which is related to 1 over the distance to the final location of the point, and I'm going to call that R. This distance here is R. That's the distance to the final location, minus 1 over the distance to the initial location. But in this case, the initial location, our reference point, is out here at infinity. It's at an infinite distance from my charge. So that distance then would become infinity. But as we all know, in the limit that we pull these things very far away from each other, 1 over infinity is in fact going to be approaching 0. So for a point charge, the electric potential formula is very, very simple. The potential from a point charge at any location is just equal to Coulomb's constant times the value of that charge Q divided by R, where R is the distance from the charge to the point where we are computing the potential.